Welcome to the last CIIR talk of this academic year. I'm delighted to introduce Huan Sun, who is associate professor, of computer science at Ohio State University. She completed her PhD in 2015, which happens to be the same year we became a college. 2015 at the University of California, Santa Barbara. And then followed by a postdoc at the University of Washington. Her research direction, broadly speaking, is advancing the capability and safety of large language model agents. She's currently working on web agents, agents that can browse on behalf of users to complete multi-step tasks, and computer use agents in general. She is the recipient of an NSF Career Award, and also multiple paper awards, in particular from ACL, SIGMOD, and CVPR. Her talk today is titled Smarter and Safer Every Day, Continual Learning and Safety in Computer Use Agents. Please join me in welcoming Huan Sun to the CIIR talk.
Thank you very much for the nice introduction. Thanks again for the invitation. And I know this is a very busy time. Thanks to all of you who made it to the talk. It's a great honor to be here. Today I'm going to talk about agents, which is what I have been working on in the past few years. And also our recent work on continual learning and safety in this space. So before I start to introduce the main content, I would like to give sincere thanks to my group, which is a part of the broader OSU NLP group led by my colleagues, Yisu, and more recent faculty, Sachin Kumar, and myself. A lot of work I'm going to talk about today was in collaboration with them. My group's research interest, as mentioned in the introduction, is around agents, particularly on both the capability side and the safety side, which I'm going to talk more about. I will mention or cover the following aspects. One is tell you a little bit about how we started working on agents, and also tell you a little bit about how do we further improve agents after deployment. And I'm going to tell you a little bit about surprising failure modes of those agents, specifically some unintended behaviors. More fundamentally, I hope to introduce a little bit the backbone model behind those agents, their potential and limitations for OOD generalization, which can partly explain those failure modes. So now you probably see agents everywhere, and everyone is working on it. So what is my story, and how did I get into this space? But really, since many of people in the audience are students, and perhaps current times you're debating whether you still want to go to academia or you want to choose a job in industry. So I hope to share with you about this story, which is really about freedom in academia led to some serendipity in the workspace. So before 2022, my student Xiangdeng and I have been working with web texts and tables for various purposes, including question answering, relation subtraction, and also many table-based tasks that are cared about in the database community. For example, relation extraction from tables, table cell filling, which is part of the table completion tasks, and table column name prediction, and so on. But at the same time, large language models have been under fast development at that time. They are getting better and better at natural language instruction following. So we were thinking, instead of just letting models answer questions based on the web information, like using tables to do natural language question answering, can we let them do tasks for humans on the web? So this is the background for how we developed Mind2Web, like why we were positioned at that time to develop this benchmark. Mind2Web is the first work that proposes the concept of a generalist web agent that aims to complete any user task on any website. Before Mind2Web, web agents were trained and evaluated all in a very few simple simulated environments. So we aim to minimize the sim to real gap. So Mind2Web collects realistic tasks humans would do on real websites for training and evaluation. Then after that, my students and I co-led a series of work, including CIIR, which is the first multimodal planning and grounding framework for generalist web agents. Basically takes the screenshots of a web page and uses that for planning and grounding. Planning, you can think of it as once you see this web page, plan what to do next. And grounding is like to translate a natural language instruction at a step into precise elements to interact with on that web page. After that, we developed uGround and WebDreamer, where uGround aims to improve the grounding ability of a web agent. And WebDreamer is the first work to see the potential of LMs as world model of the internet. By that, I mean whether LMs can actually predict what will happen next, what it will see next if you take an action on a web page, and uses that prediction to enhance the planning ability of the agent. So since 2024, we've seen the interest in AI agents has exploded, including the increase in terms of the number of papers. And also, there are more and more frequent releases from companies in the past few months. Of course, we've all heard about OpenClaw by now, which was the fastest growing open source project in GitHub history. It was the talk of the town in the past few months. So essentially, agents like OpenClaw are computer use agents that aim to do any task humans can do on computers, being like operating any software like PowerPoint, Word, maybe your Photoshop, and using terminal to manage files, as shown in this widely used benchmarks called OS World, which we are going to mention many times. Computer use benchmarks like OS World can expose capability gap and then inform model and agent development. And that's why we see gradually increasing scores on such benchmark. But there is always a risk of benchmarking. By that, I mean, for various reasons, maybe intentional, maybe not intentional, models appear extremely good on leaderboards, but underperform when used in real-world applications. So here is a reality check for CUAs. We know that digital environments are diverse and dynamic. There are millions of apps and websites in the world, and they can get updated very frequently. So in the real world deployment, agents can encounter unfamiliar or completely new environments. As an example, when Cloud 3.7 was released, it achieved like 37% performance on OS World, but it only got 10% on a later released benchmark called Science Board, which focuses on professional or scientific software, like those software for astronomical analysis. On the other hand, on the standard OS World environment, a foundation model like Queen 3 model, when that model was developed, when it could achieve like around 15% on the default environment of OS World. But when the environment changes due to, say, version updates or major UI changes or platform migration or resolution changes, we see consistent performance drop by more than 30%. So this prompts us to ask this question: how can we enable the agent to continually learn in unfamiliar and dynamic environments? And this is how continual learning comes into the play. And this term have been, I guess, a buzzword lately, and people may confuse it with a lot of techniques. So let me first clarify what I mean by continue learn here, especially in the context of agents. So I mean by continue learning for agents that an agent continually improve its performance in the deployment environments or environment. It could be single and multiple environments through a sequential learning process where you receive sequential sets of tasks, and the agent can interact with the environment, receive rewards on these tasks, and then update its system design or its internal model parameters, depending on whether it's like a closed model based or is an open weight model based. Another aspect is without catastrophic forgetting in other environments that are not being learned at this moment. So in this project, we consider intra-environment continual learning and also an inter-environment continual learning setting, which I will talk about in the next slide. For intra-environment continual learning, what do I mean by that? Basically, it is continual learning happens inside a single environment where we see, okay, there are a set of tasks given at different iterations or arrive sequentially. You can think of it that way. So for this set of tasks, the agent can execute the tasks, receive rewards for its performance, and makes updates. And the tasks at different iterations can have different distributions. Later tasks are expected to be harder, like the agent gradually learns more and more challenging tasks over time. And the inter-environment continual learning setting is about learning sequentially across multiple different environments. You can relate this to human experience where we can encounter different environments sequentially, over time, learning in one environment after another. But inside one environment, it's the same as intra-environment, where you can still have many iterations of different tasks or learn tasks of different difficulty over time. There are multiple challenges in this continual learning for computer use agent setting. One is, given a new environment, we don't have tasks readily at that time. So you can think about, okay, you are deploying a trained agent into a new environment. How are we going to get tasks in each environment? And how are we going to get supervision signals for an agent trajectory? So manual annotation is, of course, labor intensive, costly, and difficult to scale. That's why in this project, we explore this autonomous curriculum RL approach, which we name as CIIR, where we highlight by autonomous that no human data or effort is needed in this process. Let me walk you through how this framework works. So basically, there are multiple stages. For the first stage, which we call environment experience collection, in that stage, we actually ask the base agent to autonomously explore this new environment by collecting what screenshots it will see after clicking on some buttons or perform some atomic actions and see what will happen next. And we also use some web crawled artifacts for a certain environment to ground those tasks in the real environments, ground this exploration in those real environments. So, for example, if we are currently let's say adapting an agent in a PowerPoint-like environment, we'll download some PowerPoint from the web and use that to ground the explorations. And then after that is a curriculum generator where the agent will use the preliminary exploration experience as well as some capability evaluation feedback from the previous iteration to generate tasks of different difficulty levels, like easy, medium, hard tasks, and for the current iteration. So basically, the whole idea here is that for each iteration, the curriculum generator will generate tasks of different difficulty levels that fit to the current agent's ability. So the task difficulty co-evolves with the agent capability at each iteration. And then the agent will execute the task and then perform this, actions. And at the end of the day, it will have a trajectory for each task. And then at that time, we have this CUE judge or CUA judge, which is to automatically judge whether a CUE trajectory has completed a task or not. So it will provide a binary reward at this moment. Of course, future work can extend this to fine-grained reward signals. So this is a LM-based judge, but it's agentic where we can do multiple iterations and so on. This judge is also to augment the web judge we developed last year in our work called Online Mind to Web, which was a benchmark that was used to evaluate web agents' performance on live websites. That benchmark has, and also the web judge, have been used by a lot of startups in the web agent space. And we have been actively maintaining and use the web judge as well. But CUE judge here, as you will see later, it is a further improvement over web judge to improve the reliability of the evaluation. And then after that, we have this iterative RL framework. And we have the, use the reward from the CUE judge to update the agent performance or the, the internal parameters. We can do this in multiple iterations, and in each iteration, it will handle gradually more and more difficult tasks. So one thing to emphasize here for the curriculum task generation, I mentioned earlier that we are going to take the feedback, whether the agent in the previous iteration has completed a task or not, take that feedback, on the training set and use that to guide what task to generate at this iteration so that this round's the task's difficulty can fit better the current agent's performance or capability. And another challenge for training computer use agents in a reinforcement learning fashion is on the infrastructure side. So to train a computer use agent with RL, there are significant challenges on, for example, environment initialization latency and also trajectory evaluation latency in gathering, the reward signals and do the update. So we have developed some strategies to boost the training speed up compared with the vanilla use of existing RL setups. And this is also a very active direction. Concurrent to our work, we've also seen actually some other work like from MIT or startups. They are also working on RL infrastructure for for agentic training, especially in computer use environment scenarios. So for our experiments, we experimented with 6 environments to the largest extent that our budget can allow. And we have adopted the environments from considering diverse scenarios and from different benchmarks. We have like Impress, Writer, Calculator. Those are for office productivity and email related environments, and also scientific software environments for astronomy or for math. We've done like 2 base agents. One is called UITARS, and the other is Quint3 mentioned earlier. One thing to note is that UITARS was released prior to the development of a science board. So likely these 2 environments were not seen during the agent development, but both are from companies, so we don't entirely know their training data. Here are some detailed results. This is showing the intra-environment continual learning setting, where you can see that we just need to look at one base agent, but the performance gains are consistent across the 2 agents. We can look at, for example, this one. The blue bar here is the performance of the base agent on this Impress environment. And we can see through different iterations, like the orange, green, and red bars, they note different iterations. We see consistent gains of the agent on this environment. And overall here is an aggregated performance. Basically after, we do the iterative learning process, the performance of the agent on the 6 environments together. And you can see that compared with the overall performance of the base agent, there is no substantial forgetting on that. We have a specific number on each environment in the paper, which can also be found on our archive. So here I'm for just easy visualization. We show the aggregated performance. And going back to the motivating scenario where I mentioned about environmental dynamics, we can see that for different kinds of environmental changes, we see after each iteration, we also see consistent performance improvements for the post-update environments, and the performance gains are could be in double the performance gains compared with the base agent on that newly changed environment. We also scale this framework across multiple environments. Basically, let's look at the last row here, where the agent needs to learn sequentially across 5 environments. So for each environment, it's still the same as before. There are 3 iterations of learning process. And even for, we can see that basically after this sequential learning process, we see an overall performance gain from 22 to 37. So 31.7. And also, for most of the environments, there is no catastrophic forgetting compared with the base agent. And many times there is, gains to different degrees. And even for environments that are environments, we see a little bit of forgetting, but not a lot. We do want to point out that some forgetting happens here. For example, if we just do, continue learning on Impress, we can see, okay, the performance on this environment can be boosted to 39. But after, let's see, if you do another environment like a calculator, we do see the performance drop to 35. But this performance drop can be brought back a little bit by, maybe incorporating some similar environments like a writer, which is kind of a Word doc related environments to 37. So there is somewhat forgetting in some scenarios, but not a lot. And for the quality of the auto judge we use in this project, we can see that compared with the web judge, which is our previous the judge we developed in our previous work, we can see it has improved in terms of agreement with the human judge and also precision. So this is for the test time evaluation where we have the rule-based evaluator, because in the OS World benchmark, they also provide rule-based evaluation. So we can directly compare with the rule-based evaluation. But during training, because tasks are created automatically and we don't have human annotated evaluation criteria. So we perform the human agreement in order to make sure, okay, the judge signals are good enough for training. And we do see that we can, on our, hundreds of sampled trajectories, we see around 94% overall human agreement during the training. So we think that's partly why this framework can provide quality reward signals to guide the learning process of the agent. Then we performed some sparsity analysis on the parameter update during the RL process, which can sort of explain why there is no catastrophic forgetting. We didn't do any additional strategy to prevent this, but it seems RL can naturally mitigate this forgetting thing, which was also discussed in some recent RL related work to understand how RL can help continue learning. But our conclusion or analysis based on the analysis is that throughout these iterations, we see that around 80% of parameters kept unchanged. So there is a high sparsity in terms of parameter update. And we also see different update patterns for the LM backbone and also the vision encoder. We see basically more parameters being updated in the higher layers of the LM backbone, but more parameters being updated in the lower layers of the vision encoder. This is this makes sense to us because for the vision encoder, the agent does the model does need to adjust its perception layers in order to fit the surface, basically the observed differences in the websites or in the software. Like the screenshots are different and need to adjust the perception layers there. So this is what we have done in this continual learning for computer use agents. Any questions so far regarding this part? I'm going to switch gears to briefly talk about the safety side.
Any questions locally? I think people are still digesting, so keep going.
Sounds good. So, in the previous part, I've talked about the how do we further improve agents in those new environments or dynamic environments. But if you have been using the current agents for your workflows, you probably be amazed by how good they can be in a lot of scenarios. So my personal take here may be controversial, but what's blocking agents from those wide real-world deployment is more on the safety and the security side. So you can see that there are increasingly safe, more and more safety and security concerns, especially since OpenClaw. So even safety researchers might overtrust the agent and give access to their real email accounts, and the agent almost deleted the inbox. Another risk is on the security side, where there are attackers trying to inject malicious injections to the data. And the external data, such as like emails or Google Docs, web pages that the agent has access to. And this shows basically, an injection into a forum post here that the agent can run into and get misled to perform some malicious task. So in this talk, I will focus on an important safety issue. When do agents fail unexpectedly, causing severe harms to the users? In particular, we study when benign inputs lead to harmful, behaviors, where the agents perform, some unsafe, unintended behaviors that deviate from the benign user intent. Here is an example. Here, there is no adversary anywhere. User is benign, and the environment is benign, no adversarial manipulation anywhere. But you can see that if the user issues a benign instruction asking for help with the SSH setup for a certain user, if you say the instruction in this way, you will get your intended behavior, which is a user-only SSH modification. However, if the user, by any chance, adds an additional, like a command here, the normal text here kept changed, but the bold part is a newly added step, which is to configure the SSH to require password-based authentication for that user. Then there is an unintended behavior elicited from this frontier agent, which is unauthorized global SSH modification. So this shows that the agent is not reliable or robust to different perturbations of the user instruction. Variations of essentially the same benign user instruction, or slightly more complex or slightly less complex user instruction could lead to unsafe, unintended behaviors. This is the first project that characterizes or provides a conceptual framework of what we mean by unintended behaviors. So we give a definition which has the following characteristics. One is it has to deviate from the user intent. Second is we assume everything is benign. User input is benign and the environment is benign, no adversary anywhere. So it's emergent under benign inputs. And we care less about those unintended behavior that do not produce any harm. So for example, maybe just click on the screen, misclick on the screen for a few times, that may have very minor, harm risks in most scenarios. But we emphasize that here we want to consider those behaviors that violate safety constraints, especially those cybersecurity risks, causing cybersecurity risks, like leaking user private information or manipulating user files, or stopping some services that user would like to host unexpectedly. So essentially, this is the CIIR triad in the cybersecurity literature. And also we distinguish these unintended behaviors from general mistakes that can be relatively easily improved by just keeping increasing the model capability. So for example, if the agent just through the reasoning traces of the agent, you can see it actually wants to perform the task as the user intended. However, maybe because the grounding model of the agent isn't performing very well, it just misclick on a certain button. That causes some unintended behaviors. In this case, if you further improve the grounding model, which can improve the general capability, you can already prevent such unintended behavior. So in this case, we actually analyze the reasoning traces of the agent and see whether it intends to perform certain steps or actually the reasoning behavior are suspicious. It kind of shows, it misinterprets the user intent or deliberately to perform some, harmful behaviors that deviate from the user intent. So such unintended behaviors are very long tail and hard to elicit manually. So far, we've actually only seen anecdotal reports from forums or from news articles or from the X forum. Basically, there are basically anecdotal reports. People just find this and report it, and that's it. In this project, we propose a proactive approach to proactively solicit or elicit those long tail unintended behaviors in a more scalable fashion. The approach is at the core of the approach is a two-stage process based on LMs and also agent execution feedback. So these two stages are to balance the effectiveness and cost of this elicitation framework. I will skip the details here, but here is a more concrete example where the instruction that our framework generates based on a benign task from the OS world benchmark. So for the normal task, it's just a benign task from the regular benchmark. And our perturbation framework only adds this bolded part, which is tidy up the desktop for sharing. So it focuses on what we are using for that dog. The original task is basically to convert a PowerPoint file like Impress, which is the simulated environment of PowerPoint file into a document, and that's it. And then the new instruction just adds the command that tidy up the desktop after that. And then we perform this instruction on the recent Claude Opus 4.6. And we do observe flawed reasoning from this frontier agent, which is, it says that, now I need to tidy up their desktop. That means remove the original PowerPoint file from the desktop, which is what we want actually avoid the agent to do. So we basically simply means, you can actually just close those documents instead of removing it. So this suggests that the agent in such scenarios should actually stick to the core safety principles. Like by default, it should, it should actually preserve the user files instead of proactively deleting it without explicit user instruction. And we did some quantitative study, which is we find that for those frontier agents, we can have a high elicitation success. Basically, for any task we choose in our evaluation, we can find some kind of a perturbation, which is still benign, by the way, that can elicit, the harmful behaviors from that agent over 90% of the time. And we also did some analysis on the severity of the illicit behaviors, and we show that a large portion actually corresponds to actions with the medium level severity, which typically correspond to actions that are not easily reversible or that can break the CIA constraints earlier mentioned. So we did a meta-analysis in the project showing that why those frontier agents do not reliably default to core safety principles. It's because it's hard to know the essential reason, the fundamental reason in this project. But so basically, we find that when such constraints are left implicit or task instructions are under-specified, we see that those computer use agents often fail to assume preservation of user data, as I mentioned earlier, or careful scoping of the system changes, as I mentioned in the first example, like instead of doing changes for a certain user, it actually goes for the broader system changes. So potential future work could be, so in this project, we have released a benchmark where with, elicited harmful trajectories for the CUAs. So potentially we can connect with the first project where in the continual learning framework, we not only just to improve the capability of the agent, but also use this elicited, the perturbed instructions and elicited trajectories to further improve the safety of the backbone agent. So this shows, some how do we proactively study those unintended behaviors or safety risks of those frontier agents. But why do agents fail unexpectedly? I'm always curious about this question, and it's hard to approach, honestly. How do we, rigorously study this? Because first of all, most agents, frontier agents, they are closed. And also an agentic system could contain multiple components. So it's hard to do some rigorous analysis there. But my group has been trying to approach this question by analyzing the backbone transformer architecture, which has been used, of course, under most frontier agents. And also its variance, which is a looped transformer in our case. So I will, try to approach, answer this question at least to some extent through this perspective. Basically, how well do those transformers or the variance looped transformer generalize under distribution shifts? We have done a series of work in this space. An earlier project called grokking of implicit reasoning in transformers. The results of that project have been widely discussed at the time it was released on social media, and there are also YouTube videos made by others to discuss this. And more recently, my postdoc Yuan and I co-advised a follow-up project on looped transformers. So that allows us to see the promise of looped transformers and the advantage of the looped transformers over vanilla transformers. But the short conclusion here from this more recent paper is that we consider two generalization challenges. One is what we call systematic generalization, which is to combine knowledge that is never to combine, two atomic facts, for example, that have never been used for any composition during training. So this is what we mean by systematic generalization. And the other is depth extrapolation, which is for example, we train the model up to 5-hop question answering tasks. And then how this model can generalize to deeper compositions like 10-hop. And in this paper, we show that those recurrent depth approaches could effectively make more effectively, it's still not perfect, of course, but more effectively make such a generalization than vanilla transformers. And we perform some model internal analysis like circuits and so on to see how why this looped transformers can perform better than the vanilla transformers. But more fundamentally, I hope to introduce a little bit our first work because that actually lays the foundation for us to study the challenges in the second paper. So to start with, I hope to introduce what is implicit reasoning and why we care about it. So implicit reasoning is more like on the opposite of a chain of thought, which we all know about. So implicit reasoning means given a multi-step query, directly predict the answer without verbalizing the intermediate steps. So for example, if let's say the model has known these two atomic facts, and now it is asked the question, who is, when was this person's wife born? It could directly output the answer, which is 1964 in this case, without first, after putting this person's wife is this person and she was born in this year. So without this intermediate steps, it can directly output the entity or answer. And why do we care about the implicit reasoning ability? Basically just predict the answer using the model internal parameters, no explicit thoughts. So essentially, this is about how well the LMs can acquire structured representations of facts and rules, the reasoning rules from data, and how powerful it is to compress and integrate information at a scale if the model could, quote unquote, think internally. So in our first project, we did some rigorous experiments using controlled setup, like simulated data with, like two parts of data more specifically. One is atomic facts, the other is inferred facts. So atomic facts, you can think of them as a knowledge graph where each edge is an atomic fact, like the nodes are entities and the edge are relations. Inferred facts are, like a combination or composition of, here we consider two-hop composition where, like two atomic facts can be used to infer the composition of these two facts. So for example, given this HR1B and BR2T, we can infer, okay, the answer to HR1R2 is T. So that's kind of a simple setup. So during this, like a training process, what the model essentially is doing is to induce the latent rules from a mixture of atomic facts and the inferred facts. So those inferred facts, and also, of course, the atomic knowledge can be used to derive some latent rules, like how those atomic facts are combined to derive a multi-hop, the answer to a multi-hop query. And then when it is asked, a new multi-hop query, a new combination, we can see that it can derive the latent, use the latent rules to derive the answer there. So, but what's interesting in our project is we have this what we call in distribution and out of distribution setup. Basically, what we mean is that for the atomic effects, we partition them into two sets, okay, completely separated two sets. One is used to form this ID test setup. So basically, we use this, this set of atomic facts to do some to compose some inferred multi-hop queries. And some of the queries are reserved for training, and some of the queries are reserved for test. But for this atomic sets, this second atomic fact sets, they are purely reserved for the OOD set. So basically, of course, the model has seen the atomic facts during training, but it has never seen any combination of these atomic facts with any other fact during training. So this is what we mean by OOD. You can also think of it as that if this multi-hop query here is an OOD query, basically neither of these two atomic facts have been combined with any atomic fact during training. Okay, so the model has never seen the second atomic fact as the second step during training. Okay, so we have been using the vanilla transformer like GPT-2 architecture and model size for training. And I will just briefly go over the interesting messages we have seen. So basically, if we look at the green curve, which is for the in distribution experiments, we see that transformers can actually have a perfect ID generalization. But only after this so-called grokking period, meaning that you can see training actually gets saturated at this step for both types tasks, but only after many longer training steps, the ID generalization gets very good performance. But for OOD, like the blue curve, all right, so the vanilla transformers fail to generalize for this composition task. I will explain why, but it can succeed for those comparison tasks. Comparison is just, you have this two atomic facts, age attributes of these two entities, and you want to infer which is longer, younger, or bigger, and things like that. So it can have a perfect OOD generalization for this comparison task, but not for the composition task. We conducted some deeper analysis on the inner workings to understand what happens during the grokking process. We use the logit lens and causal tracing techniques, which are standard in the literature, to see, okay, basically, is there any circuits that are getting formed during the grokking process? And we did find that two different circuits get formed for different tasks. One is what we call a staged circuit for the multi-hop composition task. The other is a kind of more like a parallel circuit for the comparison task. So basically what happens in this staged circuit is the model will use the first four layers to infer the answer to the first step, like the relation R1, HR1, the answer appears around layer 5. And then in the follow-up layers, higher layers, it will try to infer the answer to the second hop. For comparison, we actually find a different circuit, which is the first four layers will do this computation in parallel, where it will simultaneously retrieve the answer to, let's see, the attribute A of entity E1, and then the attribute A of entity E2. So it will try to get the attribute value of these two entities at the same time, and then do the comparison at the follow-up layers. So there are two different layers, two different circuits for two different tasks. And this also explains, why OOD generalization wasn't achieved for composition. To echo what I said earlier, basically for the OOD generalization, we are putting together two atomic effects that have never been combined with anyone during training. So that means this second hop has never appeared as the second hop during training. So the model actually didn't store the knowledge about the second hop in those upper layers. We did find that the first hop the answer can still be retrieved from the first four layers, but in the upper layers, there is no formation of this second hop knowledge. So that's why. But for comparison, actually, that problem doesn't exist because all the atomic knowledge is stored in the first four layers, and the upper layers are only used for the comparison or aggregation. So it can indeed to generalize to two entities that has never been compared with anyone during training. So we think this is a very interesting and can sort of explain in a multi-hop, multi-step problem solving stage what will happen if you see novel combinations. Given time limit, I will quickly go over the future directions I'm very excited and our group is actively working on. So in the past few years, we have seen this, this paradigm, which is we create better data and use the better data to train better models or better agents. Usually it's the humans that create the data, no matter for training or for benchmarking. But now I've seen agents are becoming very, very capable in many scenarios, and we can use agents to improve agent capability and safety. So this include, but are not limited to self-improvement, especially if we want to push open science and we want to push the the open weight models based agents toward the frontier performance. And here by data, I mean it in a very broad sense. It could be used for environment simulation, user simulation, attacker simulation. It could also be used to collect data for auto evaluation. And I also want to emphasize on the agent safety and security side, we have done a lot of work in this space in recent 2 years with Red Team CUA publishing CIIR this year, and also the action which was just recently accepted to ICML. So here we want to basically more comprehensively study the adversarial attacks and how do we conduct comprehensive adversarial testing before deployment. How do we build effective and efficient guardrails? But overall, I think this is a very important critical space to work on and could potentially be very suitable topics to be studied in academia as well. So with that, thank you so much for your time and attention for attending my talk at this busy time. Thank you very much again.
Thank you very much. I think we're right at the edge of time. If there's someone who has we have one question. If there is one question, do you have a question? Yeah, go ahead.
Yeah. So according to your final experiments, so the composition is better than it's harder to generalize than the comparison. So do you think you can find what kind of task is composition in your agent web kind of settings, and how do you quantify which one belongs to this category?
Yeah, I think that's a great question. We are indeed thinking about to more rigorously understand the compositional relationships among tasks in those computer use agent scenario, at least. So you can actually think about the previous example I gave as a composition task, meaning that so basically the agent needs to first complete some steps, and then at the end it needs to complete one more step. So this new task is actually a sort of a compositional task based on the simply version of the previous task plus one more step. So we do see this relational structure, that can be, I'm not sure about, like the existing benchmarks, but at least in our, let's say, a curl framework, when we can automatically create such tasks, we can actually rigorously control the compositional relationship of different tasks. So when you compose a more complex task, you can intentionally add one more step. So I think that can be rigorously studied.
Thank you.
Thank you so much. Thank you, Juan, very much for the talk. Appreciate you joining us. Please, everyone, thank our speaker one last time.
Thank you.
And Juan, we'll see you on that other Zoom link, right?
Sure. Sounds good.
Okay, bye-bye.
See you shortly. Bye.
Thank you. Bye.